All right, any questions? Okay, so this is what we have been talking about for ODEs. We are going to be moving to PDEs next, partial differential equations. But we are not done with ODEs, in the sense that a lot of the PDEs actually uses what we have learned on ODEs. The single most powerful method for solving PDEs is to convert a PDE into ODEs. And we are going to be looking at how we'll be doing that. Okay, so basically solve some PDEs, and we're going to be converting our PDEs to ODEs. Right, so this is an example of what a PDE can do for you. So an example of a partial differential equation. So this is an example when people fly, typically twin-tailed airplanes, and they find out the airplane actually shakes a lot, especially at high angle of attack. So there are cases where the airplane shakes so much that the pilot actually can't see clearly what's displayed on the screens. And some of the vertical tails get shaken so much that their replacement cycle is something like 10 times more frequently than advertised. I mean, this is usually something that is found out after the design. And there is a lot of motivation on finding out why that is the case, and in future designs try to eliminate that, right? On the left-hand side, there is a flow visualization of what actually happens that shakes the airplane. What you see is that this vortex actually coming out of the leading edge extension, it seems very coherent up to here. And then it breaks down. The smoke becomes diffuse, right? And the diffuse smoke passes over the vertical tails. That seems to be creating the problem. And now this is a computational fluid dynamics simulation. And the vortex, which is indicated by this blue region inside, it actually breaks down, like in this region. And the chaotic flow that after the vortex breakdown goes exactly over the vertical tail. So a chaotic phenomenon like this has a lot of different frequencies. And as long as one of these frequencies resonates with the vertical tail, the airplane is going to vibrate a lot. So this is an example of a numerical solution of partial differential equations. What we do in this case is we have to discretize the entire space outside the airplane. Okay, we have to mesh the outside of the airplane with a mesh. Discretize the space with many millions of grid points. And the partial differential equation is going to be converted, approximated by an ordinary differential equation with, in this case, 5 variables, 5 states, 5 numbers on each grid point. So if you have a grid of, for example, 40 million grid points, and you have 5 numbers on every grid point, it becomes a 200 million dimensional state variable. So you have 200 million coupled ordinary differential equations, right? How to solve them? Using exactly what we have learned, ODE solvers, right? Except in this case, because the computation is usually so large, you are not going to be using MATLAB's ODE solvers. You are going to be studying the dynamics, the specific feature of the discretized ODE, and hand choose an ODE integrator that is most suitable, most efficient for this job. Okay, so today we're going to be looking at how to discretize partial differential equations. We're going to be starting with something much simpler than this. This partial differential equation has 3 spatial dimensions and 1 time dimension, right? We're going to be starting with PDEs with only 1 spatial dimension and much simpler grid than something we have to use here.